Let's run through multiple choice problems 7 to 12, non-calculator, on the released Calculus AB exam from 2012. Some really good stuff on here, from more calculation-based problems to also some contextual word problems. I personally think that number 8 is the one that most people will mess up or maybe not even attempt. Let's dive in. Problem 7 is one of those calculation problems that I mentioned. Here we have a function that is a composite function. Right? It has an inner piece, an inner function, this x cubed minus cosine x part. And then we have the outer function, which is raising to the 5th power. For a composite function, you're always looking for that inner piece you're doing first, and then the outer piece that you do second. Where you put the then in the sentence helps you split up which is the inner, which is the outer. When we see a composite function, we just need to think chain rule. So I'm going to take the derivative of the outer function evaluated at the inner function. So the outer function is raising to the 5th power. So if I have something raised to the 5th power, say x to the 5, its derivative would be 5x to the 4. But here we need to remember I have an inner function, so that is where I will evaluate that first piece. And the price that the chain rule makes me pay is I need to multiply by the derivative of the inner function. So I'll just write that as prime notation for now. And now let's just tidy up. So I get 5x cubed minus cosine x all to the 4. Now I take the derivative of this inner function. X cubed will become 3x squared. Cosine x will become minus sine x. And look, that's one of our answers once I tidy up that minus. It is answer E. Number 8, you'll remember, is the one that I said is kind of tricky and some people might not even know how to start it. So let's pay attention. Here we have oil being pumped into a drum. We know at time t equals 4 hours, there are 50 litres of oil. And by the time we get to t equals 15 hours, we want to know how much oil there is in total. We're given some values of a function r of t, which is really the rate of change at which oil is being pumped into the barrel. Now, when we hear something like change or net change, so the change in oil, I want us to think integral of a rate. So I know the rate at which oil is being pumped into the barrel. I want to know how much oil gets added, integrating from t equals 4 up to t equals 15. With that definite integral, we're being asked to approximate it using a right Riemann sum. And Riemann sums are to do with integrals, and integrals are to do with areas under graphs. So this is going to be the area under the curve y equals r of t as t goes from 4 up to 15. So I don't really know what the graph looks like. It might look something like this. I'll say that's y equals r of t. I know that I want to think about when t equals 4 up to t equals 15. The only thing I know about this rate is some data points from the table. Namely, at t equals 4, I know the rate is 6.5. At t equals 7, I know the rate is 6.2. At t equals 12, I know the rate is 5.9. And at t equals 15, I know the rate is 5.6. So to figure out the area under this curve, which would give me the actual precise increase in oil volume, I'm being told to use a right Riemann sum with 3 subintervals. A Riemann sum is just going to be sums of areas of rectangles. The right part tells me to use the right-hand endpoint of each subinterval. So I have my 3 subintervals, 4 up to 7, 7 up to 12, and 12 up to 15. Those are going to be the bases of my rectangles. So those bases are length 3, 5, and 3. And then I'm simply going to form 3 rectangles using the right-hand endpoint. That is my Riemann sum. So let's calculate it. So this is roughly going to be my first rectangle plus my second rectangle plus my third rectangle. If we calculate this, I'll get 3 times 6.2 plus 5 times 5.9 plus 3 times 5.6. Again, getting all this information from my rectangle formula and the information in the table. So if we calculate this, we'll get 64.9. Again, this is the non-calculator portion, so we actually have to do a little bit of arithmetic here. And oh look, that's one of our answers, right? But don't fall for the trap. Okay. This is the net change in oil. That's how much oil was added to the drum between hours 4 and 15. We need to remember how much oil was in the tank to begin with. There were 50 litres of oil there. So I need to remember that is how much oil has been added to the initial 50 litres that were there. So my answer is actually going to be C. In question 9, we're given this piecewise defined function where for every value of x except for 2, we have this rational expression for the rule. And when x equals 2, we're given a parameter value k to find. And we want to pick k to make this function be continuous at x equals 2. Let's dive in. Now notice that rational expression has a common factor, numerator and denominator, that I can cancel, right? I've got x minus 2 that I can cancel. So actually, the rule for the function when x is not equal to 2 is just 2x plus 1. So if I plot that, I know at x equals 2, okay, there's something else going on, so I'll just draw a hole in the graph there. But apart from that, I'm this nice linear function. So at x equals 2, how am I going to fill in that hole or not? Well, when x is 2, the height of this point is the parameter value, k. And the problem is simply asking us, how can I pick k so that this graph is continuous? I don't have that jump discontinuity occurring. Well, the hole in the graph lies on the linear function given by y equals 2x plus 1. So on that linear function, when x is 2, y is 5. So this tells me that if I set the height of that point just right at k equals 5, I'll fill in the hole and the function won't have that jump discontinuity. So my answer is 5. Problem 10 is asking us to calculate an area. When we see area, we should likely be thinking definite integral. So let's draw a nice quick wee graph. So the graph is y equals e to the power of x over 2. That's basically just an exponential function. I have the line x equals 2. And we want to know what area I'm bounding in that first quadrant there. So really, I'm looking for the area under this curve, y equals e to the x over 2, integrating from 0 up to 2. So the quantity I'm interested in is the integral of from 0 up to 2 of e to the x over 2 dx. Now technically, to evaluate this integral, we need to do a u substitution. Maybe you're comfortable doing that. Just in case you're not, let's do the substitution off to the side, because this is really just a linear change applied to our variable x. That's a pretty straightforward substitution. So when I take the derivative du by dx, that gives me 1/2. If I solve for dx, I get 2 du equals dx. That is what I want to replace when I do the substitution. So e to the x over 2 will become e to my new variable u. Dx becomes 2 du. But I do need to worry about those limits of the integral, right? The 0 and the 2, those are the limits in terms of x. If I don't change them, something will go wrong, okay? So when I take the x expression and convert it into u, all I'm doing is dividing by 2. 0 over 2 gives me 0. 2 over 2 gives me 1. So now I have this integral to carry out. The integral of e to the u du is one of my standard derivatives. I can apply an antiderivative. So I'll get e to the u back. My endpoints are 0 up to 1. So now I'll just substitute in e to the 1 minus e to the 0. So I get 2 e minus 1. If I look at my answer choices, I've got it factored. They don't. It's answer choice A. Problem 11 is making sure that you're comfortable working with the definition of absolute value and also with continuity, differentiability from the left, from the right, all that good stuff. Now, there are a few different ways we could approach this problem. We could think about maybe something to do with transformations or the parent square root function graph. I don't want to do that. Let's work with the calculus definitions that we're used to looking at. So I've got some piecewise brackets here to rewrite this function rule because you can see this absolute value term is going to be positive or negative depending on whether or not x is greater than 2 or less than 2. So when x is actually greater than or equal to 2, x minus 2 is not negative, so the absolute value doesn't do anything. I just get x minus 2 back, and that is what I'm taking the square root of. In the case that x is less than 2, that x minus 2 term becomes negative, so the absolute value will negate it to flip it back to being positive. So that's what happens to my absolute value term. But I can distribute that negative just to work with it a little bit more simply. So that will actually give me, oops, I actually did that twice. I negated it already. So I'm negating the x minus 2 piece. And when I distribute the negative sign, I get 2 minus x. So this is the function we're working with. The multiple choice statements are asking us to decide what's happening with this function at x equals 2. Okay, is it continuous? Is it differentiable? So on, so on. So we need to figure out some facts about this function. So let's ask it, is f continuous at x equals 2? Well, the best way to figure out what's happening there is, what are these two different rules doing as we approach 2 from above, from the right, in which case that's the rule that applies. And what happens when I'm approaching 2 from the left, from below, in which case that is the rule that applies. So let's examine the limit behavior as x approaches 2 from above of this function. Well, when I'm approaching 2 from above, it's that first rule that applies. So the limit as x approaches 2 from above of square root of x minus 2. Well, as x gets closer and closer to 2, x minus 2 gets closer and closer to 0. So we get the square root of 0, which is just 0. So as I approach 2 from the right, the function behaves like it's approaching 0. When we approach 2 from the left, it's that second rule that is deciding what the function is doing. In this case, square root 2 minus x. Well, as x gets closer and closer to 2, this also gets closer and closer to 0. So indeed, this function is continuous at x equals 2, and the value it appears to take there is 0. So we know that we are continuous. Oh, well, okay, we don't quite know the answer, but we do know that answer C is not correct because we just showed that the function is continuous. It's continuous. Is it differentiable? Let's check. So is f differentiable at x equals 2? Well, again, we're going to approach from the right and from the left and see what happens. So when x is greater than or equal to 2, if I try and, let's actually just say greater than 2, since we don't technically know what's happening at x equals 2, that's what we're trying to find out. When x is greater than 2, it's this first rule again that's deciding what the function is doing. So I'm going to take square root x minus 2, take its derivative. Okay, again, technically this is a chain rule, but hopefully you're comfortable enough just writing this down as 1 over 2 square root x minus 2, converting the square root to a half power, if you like. And just to pay lip service to the chain rule, I'll say I'll multiply by 1, because you do need to remember you're multiplying by the derivative of that inner function, which in this case is 1. What about when x is less than 2? Well, f prime of x it's the second rule that's coming into play. So I'm taking the derivative of this square root 2 minus x rule. Again, what's going to happen here is I'll take the derivative in the same way. But now, again, I need to multiply by the derivative of that inner function, which in this case is minus 1. That minus x gives me a minus 1. So if this function is going to be differentiable x equals 2, I better get the same answer from the derivative as I approach from the left and the right, the value x equals 2. These two expressions don't look super equal. They might be, but you can see pretty quickly that they're not equal, because one, the top one, is positive. The other one, the bottom one, is negative. We're multiplying by that negative 1, and that fraction in both cases is just a positive number. So because we have different answers for f prime as we approach x equals 2 from the left and the right, the function is not differentiable. So you can see the answer is A, because we showed we are continuous but we're not differentiable. While I have you here, we may as well run through the other choices. Okay, B is not differentiable. So, B says the function is differentiable. We just showed that it's not. In evaluating continuity, we showed that the limit of the function as x equals 2 did equal 0. Part E is trying to trick you, I guess, and is hoping that you maybe think asymptote looks like a tangent. I'm not sure, but there is no asymptote in this graph. X equals 2 is in the domain of the function, so it's not giving us a vertical asymptote. There's no infinite behavior as we approach x equals 2. Final problem of the video. Problem 12, we're being asked to rewrite a definite integral using substitution, and we're even given the substitution. Can't get better than that. So we're given the substitution u equals the square root of x, and remember the square root of x, if I want to differentiate it, we can write as the x to the 1/2 power. So du by dx is going to be 1/2 x to the minus 1/2, which is 1 over 2 root x if we rewrite that. So I'm trying to rewrite this integral, not in terms of x, but in terms of u. So notice I have dx root x hanging out there in the denominator. You can see here I have a root x hanging out in a denominator here. So if I rearrange this equation that I'm working with, I'll get 2 du equals dx over root x. Just multiplying factors to move them about in the equation. I've done that because dx over root x is what I see in the integral I'm looking at. And so I know when I do the substitution, I can replace that with 2 du. So let's rewrite this. I'm going to get e to the root x. Oh, well, that's just e to the u. That's nice. The dx over root x, I'm going to replace that with 2 du. The last thing I haven't talked about yet is the limits of the integral. We need to remember to change those. The 1 and the 4 are the limits in terms of the x variable. We need to convert to being in terms of the u variable. So you can maybe do this in your head, but it's sometimes nice to throw down a wee table. So when x is 1 or 4, u is just the square root of x. So the square root of 1 is 1, and the square root of 4 is 2. So that tells me my limits are 1 and 2. Hopefully this is one of my answer choices. You can see I need to tidy it up a little bit. I'll pull out that constant 2. But this is what we have. And this is answer choice C. Done. So another 6 multiple choice problems in the books. Awesome, great job. If you missed the first 6 problems, you can find them in this video here. And if you want to look at the next 6, here they are. Let me know how you got on. What did you think of that Riemann sum one? Which did you think was the trickiest? Love to hear from you in the comments.